Hello everybody, my name is Justin Balsley, and I did my research on the evolution of flight. The importance of flight cannot be overstated in today's society and throughout history. From Leonardo da Vinci's ornithopter, the Wright brothers' device or invention called the flyer, and even from many historical people such as Amelia Earhart. The ability of flight has shaped the modern world, and it's helped give access to once inaccessible areas and has connected us all globally. There are several different species that have discovered this, because us humans aren't the first ones to come across flight, and we were inspired by many of those of our ancestors before us. These include the pterosaurs, the avians, chiropterans, and winged insects. Each of these insects, or each of these species, which is actually very cool, they all develop this ability separately, on their own accord and on their own time. To begin our discussion, I will first go through the theories of flight with invertebrates. First, we have the arboreal model of flight. This theory suggests that flight developed in a tree-dwelling ancestor that was built for gliding, but started flapping to extend its airtime. So as you can kind of see here in the picture, you have a species that over time would develop flight through the power of gliding, which is very cool, I think, personally. Next is the cursorial theory. This is the ground up. And so this theory suggests that flight developed from bipedal species that ran along the ground and were assisted in leaping with the help of wings. Lastly, we have the theory of sexual selection. And this suggests, as you may have learned, that the development of feathers and wings was not an advancement of natural selection, but instead assisted in a particular species' ability to mate. Unfortunately, regardless of how compelling this theory might be, it's impossible to test, and thus it has not been pursued much further. Now we have the theories of flight in invertebrates. There are two common theories. First, the perinodal origin theory, which concludes that the growth of wings from insect species developed via an outgrowth upon the tergum, which are lobular outgrowths on the thoracic segment. In addition, we have the pleural origin theory, which bases the evolving of wings via the pleural region of the thorax. In other words, wings develop from the remains of gills or other breathing apparatuses from once aquatic species. The first species we'll discuss is the pterosaur. The pterosaur is the initial vertebrate to have evolved to the capacity of powered flight. They developed this capacity around 225 million years ago, and they went extinct around 145 million years later. They were related to both dinosaurs and crocodiles. It's speculated that pterosaurs evolved through the cursorial theory, which we just discussed, and this is because their legs acted in a pole vaulting manner, shooting them from the ground up. Now we have pterosaur phylogeny. Pterosaur, or Pterosauria, shown here, developed from Ava metatarsalia, which is a common close ancestor to Crocodilomorpha, or crocodiles. Ava metatarsalia gave way to both Dinosauromorpha, or what we know as dinosaurs, and the Pterosauria. Although what is not shown is the intermediary to Pterosauria. And it is thought to be a taxa called Diapsida. This is because of certain holes that are found in the skulls that are common to both of them. Nonetheless, this gives no indication of a particular development on how pterosaurs gained wings for flight. The pterosaurs have a small body, hollow bones, and large wingspan. They possess 4 digits, 3 of which were not attached to the wing, and 1 of which composed of a large majority of the wing. The wings were composed of this tough fibrous material, with its own unique circular vasculatory system that supplied all of the wings. Now, moving on to the next vertebrate species to have developed flight, we have the avian group. The avian group consists of an exhausting number of different species. It's widely accepted that birds have evolved from dinosaurs. Specifically, they evolved from a group of dinosaurs called theropods, which are your velociraptors and such. Birds came into existence through an intermediary that lived around 150 million years ago, which is within the mid-Mesozoic era. The intermediary, Archaeopteryx, was a very significant discovery because it helped bridge the gap between what we know today as modern birds, also known as Neo-Ornithines, and dinosaurs. Another significant discovery was also the Maniraptor, not shown, which helped give a better understanding of how dinosaurs came to be the Archaeopteryx. Although it was not an overnight process from dinosaurs to Archaeopteryx, because in actual the development process was very slow, millions of years, 50 million at the fastest estimate, and that's just to take the theropods, which include the Velociraptor, down to the proper size. However, once the Archaeopteryx finally gained its ability of flight, it flourished. And it flourished through the Cloud Aves, shown here, and to what we know today as the modern bird, which is the Neo-Ornithines. The morphology of the avian species is very fascinating because it was discovered that the Archaeopteryx actually closely resembled the embryo of the Theropoda. So it's as though they formed through a lack of development. The Archaeopteryx did go through major change shifts, including the elongation of the second phalanx and the bending of the wrist here to help give the more common bird wing shape. Other major advancements for the Archaeopteryx was the development of hollow bones, which was also common in a pterosaur, and the development of feathers, which the pterosaur also had fibers that helped with the aerodynamic flight efficiency as well. The Archaeopteryx was far from an ideal flyer though, due to an inefficient muscle attachment point on the sternum. Many changes were underwent from the Archaeopteryx to modern birds, including the loss of teeth, developing a curved sternum with a keel for better attachment points for the muscles, and changes in the flight pattern. It is worth noting that the bipedal movement and the feathers that you see in Neo-Ornithines today is that they actually first developed in theropods, or dinosaurs, such as velociraptors, first, and this was seen as the beginning transition point to the avian community. Now we have the remaining vertebrate to develop flight, the Chiroptera, also known as bats. Bats are believed to have first developed flight around 70 million years ago. It is difficult to ascertain a true rate of time, but there is a lack of archaeological evidence for bats. There are several theories, though, as to the origin of bats, but they all seem to stem from the same idea that bats originated from the tree-dwelling glider. It is commonly thought that Chiroptera are close relatives to the order Dermoptera. This order includes a species such as Colugo, which is arboreal in nature, which helps give credence to the idea that bats derive through an arboreal model. It's difficult though because there was a major extinction event around 15 million years after the initial evolution of bats, which eradicated the majority of the species of the Earth at the time. There are two orders of bats, and that's the Megachiroptera and the Microchiroptera, with each classification only loosely relating to size. Carl Linnaeus, who was the father of taxonomy, noted a peculiar similarity between Megachiroptera and the ape species. As a result, he originally grouped bats with primates, which helped give a realization to the difference of Chiroptera and birds. This relatedness to primates gives the impression that there may have been a period in which mammals developed flight a second time, which lends credence to the flying primate hypothesis, which posits that Megachiroptera drive separately than other bats through the development of flighting primates. It's very debated though. Bats are very different from the other species we talked about because they have 5 phalanx digits that all contribute to flight. These phalanges are exceptionally long and well suited for flight. Between each of them is a thin membrane that helps create a pressure differential that is necessary for power flight. There are several similarities to other flying vertebrate groups as well, such as slender hollow bones, a light body construct. The chopper provides scientists with a very unique understanding of flight. Lastly, we have the only invertebrate to develop flight, the insect. They developed flight around 325 million years ago during the Carboniferous period. It is about 100 million years after the first insects initially appeared. There isn't a huge amount of archaeological evidence because of the fragile nature of the insects. So this gives us a hard time with phylogeny. But it is understood that they did come from Hexapoda, which are six-legged insects. The original insects had fixed wings that were incapable of folding. However, the folding capability was developed not long after, comprising the order Neopterus. After these slight changes, there really hasn't been much anything drastic that's occurred from those few 100 million years ago until now. We have already previously discussed the two origins of theories for the development of flight. And they all kind of differ among the different insects of their shape, texture, structure, hardness, Venus distribution. But their origins still kind of show the same exoskeletal development. What is very unique about insects and their wings is the vast uses of them, from protective covers, thermal collectors, gyroscopic stabilizers, sound producers, visual cues, and of course flight. In conclusion, I would like to note some of the key differences that are seen among these different species, including the phylogeny coming from reptiles, mammals, and reptiles creating an entirely new subset of avians. Furthermore, we have differences such as feathers, no feathers, and then just hair on the bats. Even more so, we have the changes in digits, which are different from them all. And even the different attachment points of the muscles are all unique to these different species and the way that they fly. Now, despite their vast differences, I find it more amazing that they all have some common elements to them each, including slender bodies, their light construct, and their vertebrae, which are a specialized system of strong and hollow bones. It's crazy to imagine how such a complex and awe-inspiring development of flight has developed several times throughout all these different species on their own path. Thank you all for listening. This is Justin Balsley once again with the evolution of flight.